My slides are visible to you.
Yeah. So let me introduce Anju. So Anju is a senior research fellow in physical research laboratory working with Professor Artishi. Her interest is in quantum optics and quantum information. So today's title of her talk is Discrete Modulated Continuous Variable Quantum Key Distribution over Free Space. So stage is yours, Sanju. You can start.
Okay, thanks for the introduction. I am Anju. I'm a senior research fellow in Quantum Science and Technology Lab and doing my PhD with Professor RPC. So the title of today's discussion is Discrete Modulated Continuous Variable Quantum Key Distribution over Free Space. So this is the outline of today's talk. I will first start with the introduction to quantum key distribution. Then I will study the different classes of QKD protocols. I will explain in detail one of the protocol parties who want to communicate with each other and they send some messages. So the process looks simple, but it is not that simple. Or is it secure too? So what if a third party is present in between and had the information? So what should we do in that scenario? So sending the message directly is safer or not? So here comes the idea. So if we convert this message in some another form and only the two parties, that is sender and receiver, they know how to retype back the message from this encoded version, then the process become more secure. So this process of secure communication is known as cryptography. So at present, we are using classical cryptography techniques, and the classical cryptography technique include the process of encryption and decryption. So in encryption, we have a plain text that is the original message. We attach an encryption key with the message. What we get is the cipher text, and the cipher text is transmitted through the channel that could be Wi-Fi, LAN, or free space. So this cipher text is again converted to the plain text by using a decryption key. Now, based upon this encryption and decryption key, the cryptography is broadly classified into two sections. One is symmetric key distribution and another is asymmetric key distribution. In symmetric key distribution, both parties, that is Alice and Bob, they use the same key for the encryption and decryption purpose. Whereas in asymmetric key, both parties use different key for encryption and decryption. So the question is, what limits the classical key distribution protocol? First thing is unconditional security is not possible. So the current classical cryptography technique, they are based upon the complexity of the mathematical algorithms. So once there is enough computational power, security could be compromised overnight. Another disadvantage is it is not possible to detect the intervention due to third party. And we are now lying in the era of quantum computers. So it is very essential to make the process secure. So here comes the role of quantum key distribution protocol, where the security is completely relies on law of quantum mechanics. And it is another advantage with QKD is that the presence of an adversary could be detected by looking at the error bound for different protocols. And these QKD protocols provide unconditional security in principle. Now, how a QKD protocol runs? Let's have a brief idea. So basically, we have again two parties, Alice and Bob, that want to communicate with each other. So the key information is encoded in the quantum state of light, and that is the state is transmitted through the channel. The channel could be fiber or free space. And at the receiver end, detection is performed by Bob, and the detection could be like what type of protocol is used. So we can perform single photon detection, or we can perform homodyne detection to measure the field quadratures. So once the key exchange process is done, they use classical authenticated channel to further get the secure key. Coming to the classification of QKD. So QKD has been broadly divided into two major sections. One is discrete variable QKD and another is continuous variable QKD. Both are further divided into subsections based on prepare and measure protocol or entanglement based protocol. Like discrete variable QKD has again various protocol like BB84, B92 that belongs to prepare and measure, and BBM92 and QIQT23 that belongs to the entanglement based protocol. So another class is continuous variable QKD, that is the area of interest of today's talk. That is again further divided into prepare and measure and entanglement based. So we'll discuss in detail about this prepare and measure continuous variable quantum key distribution. which is further classified into Gaussian modulated CVQKD and discrete modulated CVQKD. So before going further, first question is why CVQKD? Because we are already people has demonstrated discrete variable QKD over hundreds of kilometers, thousands of kilometers. So why CVQKD? So CVQKD doesn't require single photon source. It is easy to integrate with available classical infrastructure. It provides much higher key rate compared to TV at particular distance of hundreds of kilometers, and operate at very high bandwidth with higher detection efficiency even at telecommunication wavelength. So the current state of art of CV is that it has been demonstrated over hundreds of kilometer distance using fiber link, and is proved to be one of the best possible candidate for metropolitan area network which are highly populated or highly dense area where high key rate is required. So now coming to the introduction of CVQKD. So this CVQKD uses coherent state as the state basically. So the coherent state are the state that have well-defined amplitude and phase, and they are bounded by the Heisenberg uncertainty relation with minimum uncertainty. This Q and P, which these are amplitude quadratures and phase quadratures. So the key information is encoded in these quadratures of the coherent state. Now, based upon the modulation scheme, we can further divide them into Gaussian modulation CVQKD and discrete modulation CVQKD. This Gaussian modulated CVQKD, both Alice encodes the key information in quadrature Q and P, and they are selected from the independent identical Gaussian distribution. And at the end, both Alice and Bob, they are left with correlated Gaussian data. So key is not obtained directly in binary form, but we use some post-processing algorithms to convert the decimal numbers into the binary, or to convert the Gaussian distribution back to the binary key. So these protocols provide much higher key rate, but they are difficult to implement and work good for higher SNR. Another class is the discrete modulation CVQKD. These are easy to implement and could be implemented. Key information is directly obtained in the binary form, and another advantage is that there's we can use discrete phases or amplitude to encode the key information. Both of these classes uses balanced homodyne detection to retrieve back the quadratures. So before moving further, let's have a brief discussion about balanced homodyne detection. So what is balanced homodyne detection? We have a beam splitter and we have two input fields A and B. They interfere at a 50-50 beam splitter, and we use two photodetector and obtain the subtracted photocurrent I. This two fields, one is known as signal and another is local oscillator field. This local oscillator field is nothing but a strong classical beam. So this is the subtracted photocurrent that we obtained. And now if I associate phase with any of these, so let's say I associate phase with the local oscillator, then this photocurrent I get the form of this. So this I phi is the observable we are actually interested in, and we measure during this balanced homodyne detection. This is nothing but the photocurrent. Now, how this photocurrent is related to the quadratures that we are talking about. So if we calculate the expectation value of this I phi, this would be nothing but the rescaled quadrature value, where this x phi is having form q cos phi plus p sin phi. Now, this phi would provide me information of quadrature q or p that is associated with the signal. So if phi is 0, I would get information about quadrature q, and if phi is 90 degree, I would get information about quadrature value p. So this is the quantity of our interest that we measure during homodyne detection and with the rescaled photocurrent output. So this is an overview of a general CVQKD protocol. So again, we have two communicating parties, Alice and Bob. We use a laser source. We modulate the signal, and that modulation could be Gaussian modulation or discrete modulation. That could include both amplitude and phase modulation, or simply phase modulation techniques. So this signal is encoded and then transmitted through a quantum channel, and at the receiver end, balanced homodyne detection is performed at a 50-50 beam splitter, where this signal and the local oscillator, they merge, and we get the subtracted photocurrent. Now, based upon the angle of this local oscillator or phase of the local oscillator, we can get the we will get the quadrature value q or p at a time. And this is how the key establishment is done in CVQKD protocol. We further do post-processing using authenticated classical channel, and the post-processing includes shifting where both Alice and Bob are left with the similar basis. Then we do the parameter estimation. The process of parameter estimation generally include the channel transmittance and the excess noise, which are very important parameter for the execution of CVQKD protocols. The next step is the reconciliation and then privacy amplification. And after this step, we get the final secure key root. This is one of the class of CVQKD that we will discuss in detail today. That is discrete modulated continuous variable quantum key distribution, easy to implement. Key information is obtained directly binary form. So Alice, how the encoding and decoding in this protocol is done. Let's have a look at it. So Alice randomly chooses one of the 4 phase value corresponding to state alpha, iota alpha, minus alpha, and minus iota alpha with phase value 0, 90, 180 to 70. So she assigned bit value 1 to the phase value 0 and 90 degree, and bit value 0 to phase value 180 and 270 degree. So once the encoding is done, the state is transmitted and Bob receive the state and perform balance line detection. So he measured the photocurrent output that is directly related to the quadrature value, and based upon the phi, that is phase associated to the local oscillator at the receiver end, that is at the Bob end. So he would get either quadrature Q or quadrature P. So once the state is transmitted and state is measured, they will do the basis shifting. So what is done? So if Alice encode her state in Q basis and Bob measure her state, his state in Q basis, they will assign it as a correct basis measurement. And if Alice sent her bit in Q basis and Bob measure in P basis, they will assign it as a wrong basis measurement. So this is how they do the shifting. So they calculate the relative phase phi, and these are the 4 phase values corresponding to the relative phase. They plot the probability distribution of the quadrature output for these 4 phase values, and these are the distribution. From the graphs or from the probability distributions, we can see that distribution corresponding to 90 degree and 270 degree, they are identical. And at this moment, Bob cannot distinguish whether the state belongs to 90 or 270 degree. So they discard these 2 distribution values. Now they are left with this 0 degree and 180 degree. So this blue line corresponds to 0 degree. And this one yellow line corresponds to 180 degree. So these are the distribution that correspond to the key part formation. So the question is, these are the probability distribution and they are in terms of numbers. How the bit value is retrieved? So from these 2 distribution, we can see that there is some common reason where both it is difficult to say whether this state belongs to 0 or 180 degrees. So this reason is known as inconclusive measurement, and this so they have to decide a threshold value to eliminate. Bob has to decide some threshold value to eliminate this reason. So if the quadrature value x of 5 that is greater than this threshold value, so he will assign it as a bit value 1, and if this quadrature value is less than of this threshold value, then he will assign it as a bit value 0. This is how both Alice and Bob, they get a sequence of key after shifting. So the 2 important parameters here are bit error rate and post selection efficiency. So bit error rate is nothing but the error that this reason that correspond to the error in the key, and post selection efficiency is the final the part of the distributions that correspond to the final key. So we perform some simulations to account the channel transmittance and the excess noise introduced in between the channel. And these are the probability distribution that these are the simulated probability distribution that we get after the noise model. From the distribution, we can see that they should have identical variance. There should be 0.5 for each one, and the value differ a bit due to the noise introduced in between the channel. And the variance is the security parameter for these CVQKD protocols. Also, this post selection efficiency and bit error rate, they are function of threshold value as well as the mean photon number. And these are the 2 graphs for this PSC and bit error rate as a function of threshold and mean photon number. From the graph, we can see that as we increase the mean photon number, the distribution gets separated apart. And at that moment, post selection efficiency would increase and bit error rate would decrease. And if we decrease the mean photon number, the distribution would come closer and bit error rate would increase and PSC would decrease. So from the graph, it is important to get a trade-off between mean photon number and threshold value to get efficient key rate. So moving further, we calculated the secure key rate and we calculated the mutual information, and the formula is given in this form. And this graph gives us the secure key rate with distance. And from the graph, we can see that even for higher excess noise, the protocol is feasible up to distance of 30 to 35 kilometers with the given parameters. And these studies would help for the experimental implementation in field and to verify the parameters. So coming to the experimental part, this is the experimental demonstration of discrete modulated CVQKD protocol. So we use a pulse laser source operating at 1 megahertz and 30 nanosecond pulse width. We set a Mach-Zehnder interferometer. One of the arm of the interferometer is controlled by Alice, that is signal, and another arm is Doppler oscillator, which is controlled by both. We use electro-optic phase modulator to modulate the phase of Alice as well as both. So we drive this phase modulator are basically high voltage devices with the V5 voltage of 170 volt. So we drive this phase modulator using a high voltage amplifier that is driven by this AWG, arbitrary waveform generator. So a random pattern of 4 phase value corresponding to Alice is generated using this AWG and fed to this PM. Similarly, a random voltage sequence of 2 phase values corresponding to this PM that correspond to both is fed, and the final homodyne detection is performed at this final BS. So this is the whole setup, and moving forward, first step, these are the experimental results. So first we do the initial characterization of the setup that includes the linearity test of the individual photodetectors and the linearity test of the short noise. So to perform the measurements, we block the signal arm and we don't perform any modulation. We just have a local oscillator at the input of this BS, and the beam is divided equally, and the subtracted photocurrent is obtained, and the voltage corresponding to the each photodiode is plotted here, and which show that both are behaving in a similar manner. And this is the graph for short noise variance, because we are calibrating everything in terms of short noise units. So the linearity test is very important parameter. So this is the probability distribution of homodyne out quadrature values that we obtained experimentally. This red and blue correspond to phase value 0 and 180 degree, whereas black and green, they are distributions corresponding to phase value 90 degree and 270 degree. And now these are the experimental parameter, and we calculated the secure key rate for a particular execution of the protocol. So channel transmittivity is 0.9, overall detection efficiency is 0.76, and the laser operate at 1 megahertz, and this is the short noise unit we defined. So we process 81,000 signal, and we get half of the we get shifted key, that is half of the processed signal. We calculated the post-selection efficiency and quantum bit error, and this is the final secure key rate that we obtained experimentally from our executed protocol. So with this, I'll summarize. So we discussed different classes of CVQKD, and we demonstrated a real-time discrete modulated CVQKD protocol in our lab, and we studied the effect of various parameters on the secure key rate. And these are the ongoing study, like we are doing field demonstration of free space Gaussian and discrete modulation CVQKD. And we are trying to optimize the parameter for field demonstration. So this is the work we have performed in our lab. So we demonstrated both discrete modulated and Gaussian modulated CVQKD over a distance of 5 meter in our lab, and a demonstration of field demonstration up to a distance of 35 has been done successfully. So with this, I would like to thanks, and I'm open to the questions.
Yeah. So Anju, thanks for this nice presentation. So now our session is open for few question. Is there any question you can ask to Anju?
Thank you for your talk. I have few questions. So first one is, how do you generate 4 states? I think these are sometimes people call compass states, right? Or maybe I am confused. So
So basically, the four states are generated like we are using electro-optic modulator and they are phase devices, like they are voltage devices. So if we will feed a particular voltage, that would correspond to phase, some phase change. So like these phase modulator have some characteristics that vary from -pi to +pi. So if we'll give a particular voltage, that voltage would correspond to any phase value. So I can show you one. So this is like this is how the random phase values are generated. So this correspond to phase value 180, this correspond to 90, this correspond to 270, this correspond to 0. And this is the random sequence generated for both. So this value correspond to 90° and this value correspond to 0°. So basically we are playing with the voltages and that voltages will feed to the PM and it will just move one wavelength cycle. So we are working within one wavelength cycle.
So this, it means that it is a sum superposition of four coherent states, right? Your state.
Not exactly superposition. We are selecting one state at a random at a time.
Ah, okay. So this
Yes,
is not
yes.
a compass state. So
No,
this
no,
is
no.
like,
We are
so there is
selecting
no
one
interface.
at a time. Yes, yes.
Okay. Okay. Thank you. So at what frequency you are generating these coherent states for?
So our laser is operating at 1 megahertz. So we are generating a signal of 1 microsecond that matches to our pulse, I mean laser repetition rate. So we are generating at 1 megahertz. We are performing modulation at 1 megahertz.
So do you use any nonlinear element in your setup?
The electro-optic modulator, they use lithium niobate crystal, like the lithium niobate crystals basically. And no such nonlinear processes in directly.
Okay, so my last question, can we achieve the same effect by considering two coherent states?
We can. Yes,
Okay,
it is possible. Like we can use 0 and 180°. That is more simpler. But as you keep on going to the higher states, we will get more key. Like we can go up to 8-phase modulation scheme, 16-phase modulation scheme. As you keep on going up, so key rate would increase.
Thank you.
Is there any other question? We have a couple of minutes left.
Maybe I will. You mentioned about space cryptography. So I think I did not hear any space part in your discussion. So what kind of like noise effects you are considering in the space part?
Actually, we are currently doing this field demonstration, and while going to the field demonstration, like as I said, the important parameter are transmittance, like there is effect of the environment, and another thing is the excess noise, like you have I haven't shown in my slides. So there could be different possible errors, like modulation error, atmospheric error, like turbulence, and all these parameters. So while performing field demonstration, we need to account all these parameters, and like key rate is extracted in terms of the atmospheric turbulence.
So what is the key rate, sorry, in your case?
I have shown for the demonstration only, like key rate is 0.35 bit per pulse in the laboratory setting. For field, we are processing the data.
Thank you.
Thanks again, Anju, for this beautiful, nice talk.